So we know now that matrix multiplication is not what we thought it was. Its properties or the way we multiply with matrices is not the way we add or subtract matrices at all. So there are some warnings and some properties that we need to consider. And the goal here is not for us to memorize these properties. The goal is for us to understand the properties and learn how to think and reason about other properties. So if we say, well, can I do that? Where does one turn to answer that question? And in short, we either have the property listed or we can reason through why or why not the property may or may not be true. So the first thing we should point out is that in general, it's not true that A times B is the same thing as B times A. A plus B or is the same thing as B plus A. The commutative property holds on addition, but the commutative property does not hold on multiplication. So no commutative property. And the easiest way to imagine this is that for number one, suppose that A is a 3 by 5 matrix. And suppose we're going to multiply it by B, which is a 5 by 2 matrix. Well, we're going to get some new output from this, some new matrix that we'll refer to as C. And because the number of columns in matrix A is the same as the number of rows in matrix B, we expect the C matrix to exist and to have a dimension of 3 by 2. Now, if you reverse those and you say, let's try and take B times A, well, B is 5 by 2, A is 3 by 5, and you can see that the number of columns here does not match the number of rows here. In fact, if we thought about this as having 2 columns, and we thought about the second matrix as having 3 rows, well, these two elements have columns that they could scale, but what about the third one? And so we clearly see that B times A is not going to exist if the dimensions are not square. Now, what about if A is 1, 2, 3, 4, and B is 0, 1, 1, 2? Well, in this case, if we multiply it this way, we're going to get 0 times the first column plus 1 times the second column, which will give us 2, 4. 1 times the first column, which is 1, 3, plus 2 times the second column, which is 4, 8. 1 plus 4 is 5. Let's see. 3 plus 8 is 11. So that's the product we get one way if we call this A and B. Now in this case, since they're both 2 by 2, reversing their order is not going to make the product impossible. But let's see what happens. Now we're scaling different columns. And that's really the key here. Here we were scaling the columns 1, 3, and 2, 4. But here we're scaling the columns 0, 1, and 1, 2. So already we can tell that we're not doing the same thing. In fact, when we take 1 times 3, 1 times the 0, 1 vector and 3 times the 1, 2 vector, we are going to get, 1 times 0 plus 3 is 3. And already we're done. Already we can see that just the first element alone is going to be different. 1 times 1 plus 2 times 3 is 7. 2 times 0 plus 4 times 1 is 4. 2 times 1 plus 4 times 2 is 10. And these are not equal. So even when it is possible to reverse the order of multiplication by virtue of dimension, does not necessarily mean we're going to get the same matrix. Now there are some exceptions to this. You can find matrices that will do this, but in general it's not true. So we cannot just take a gamble. Also, here's an interesting property. Normally when we would say that if 3 times x is equal to 3 times x in working with real numbers, we could make the conclusion that this, or let's say this is x times y, we could make the conclusion that x equals y. But it's not true that if you have a matrix A and you multiply it by some matrix B, and you get the same result as when you take that matrix A and multiply it by some matrix C, that it's true that B equals C. A really simple and quick example, which looks at, say, A is, so for property 2, if A is the matrix, let's say 0, 0, 0, 0, if this is A, and B is any other matrix, let's say 1, 2, 3, 4, what are we going to get? Well, we're going to get the 0 matrix because we're going to be scaling vectors in here that are 0 vectors. So we'll end up with the matrix 0, 0, 0, 0. Now let me also take the same matrix A, but let me multiply it by some different matrix B, which is 7, 8, 2, 6. And in this case, I'm also going to get the 0 matrix. And clearly we get the same result, but B and C are not the same matrices. Now I picked on the 0 matrix, but it turns out that you can pretty much find other examples where this works. So you just cannot conclude that B and C are the same. If a product AB is the 0 matrix, you cannot conclude in general that either A equals the 0 matrix or that B is the 0 matrix. Again, you can find special exceptions to this. I think we can construct one if A, let's see if we can get the 0 matrix. How about we do 1, 5, 0, 0, and then we multiply that by, we'll say 0, let's go with, let's try this. We'll try -5, 1, 0, 0. So in this case, -5 times 1 is -5, plus 5 is 0, and -5 times 0 plus 0 is 0. So far we have a 0 product in the first column, and now we're taking 0 scalars and scaling them by non-zero vectors, but that's just going to give us 0, 0. So you see here that we have two matrices A and B that are both non-zero. They're not that neither is exactly the 0 matrix, and yet when they multiply together, they do produce the 0 matrix. So interesting features, and this is because of the way we multiply it. The fact that we're taking A and we're multiplying A by all of the columns of each of the columns of B, that idea of vector matrix multiplication makes this property a little bit different. Now, in this argument, we're going to say that A is an m by n matrix, and B and C have sizes for which the indicated sums and products are defined. So the associative law, we won't go through this specific proof, but the dimensions, we'll make kind of a dimensional argument. Let's say that in property A, that A is 2 by 3, B is 3 by 4, and C is 4 by 2. So if we were to multiply first, if we were to say that multiplying B and C together and then multiplying that result in front by the matrix A would give me a 2 by 3 multiplied by a 3 by 4 multiplied by a 4 by 2. Well, what's going to happen inside here is we'll get a 3 by 2, and now we're taking a 3 by 2 and pre-multiplying. I'm going to start using that word pre-multiplication because we can't just stick A anywhere we want. A did not commute, it did not move, it's still in the front. It's just, it's going to multiply the result of the product of B and C. So here we would get a 2 by 2. Well, what if we took a 2 by 3 times a 3 by 4 and then multiplied that by a 4 by 2? Well, do the parentheses first, we'd get a 2 by 4, and then we'd multiply that by a 4 by 2. So at least dimensionally, we would end up with the same dimensions. So the dimensions would be equal to one another. And we'll stop there. That's not enough to prove this associative law, but at least it gives us a sense of the dimensions will still work out. If the dimensions didn't work out, we have a problem. Now here we have two distributive properties. And it's important to distinguish between them because we have a left and we have a right distributive law. B essentially says that as long as you don't rearrange the order of multiplication, that is, A stays in the front when it distributes, that A times B, A times C, those two products added together will give me the same thing as adding B and C together first and then pre-multiplying by the matrix A. That's as opposed to the right distributive property. As long as you remember that you cannot commute, you cannot push a matrix past another matrix in terms of a product taking place between those two matrices, then everything will work out fine. B plus C times A. Now you can't move the A matrix to the front because it may mess up the dimensions. If B and C are both, say, 3 by 5, therefore A would have to be 5 by something. We'll say 5 by 2. Now if I moved A in the front, now I'm going to get an inside dimensional mismatch because the 3 and the 2 are not going to, there's not going to be an equal number of columns and rows. So in the right distributive property, we can distribute from the right, but we have to distribute and keep that A matrix on the right-hand side of everything that it multiplies. And in that case, you can see B times A is still a 3 by 5 with a 5 by 2, and C times A is still a 3 by 5 with a 5 by 2. And therefore, we can still say B times A plus C times A. So as long as you don't commute that matrix to the other side of the matrix that it is multiplying, we're in good shape. And you can see here that this is going to be a 3 by 2 plus another 3 by 2, which is the same thing we would get as if we added B and C together first, giving us a 3 by 5, and then multiplying it with a 5 by 2 to give us a resulting matrix that is 3 by 2. D is kind of one of those cases where a scalar, if you have a scalar R, that scalar, it doesn't matter which matrix it multiplies. You could multiply A by that scalar and then do that product with B, or you could distribute pass the scalar in and out, basically. We can say that scalar can be anywhere that it wants to be because it is not a matrix. It's just a whole number. Finally, in this property E is an interesting one because it incorporates this thing called the identity matrix. And the identity matrix, that is I sub m, is well, I'll give you an example of an I by 2 or an I2. The I2 identity matrix is this matrix here that probably looks somewhat familiar when we perform Gaussian elimination. And it doesn't matter what matrix you multiply this by. We'll just give a general example or a specific example here. And let's say we multiply this A matrix here by I2. Well, we're going to take 1 times the first column and add that to 0 times the second column. Well, that just means we're going to return the first column. Now we're going to take 0 times the first column plus 1 times the second column. Well, 0 times the first column is the 0 vector, plus 1 times the 3, 5 vector is just the 3, 5 vector. And we end up with exactly the original matrix that we started with. And it turns out that it doesn't matter where that matrix is, and this is the exception to that ABBA rule. The identity matrix is this special matrix where it doesn't really matter where you put it, which side you multiply it on. In this case, we'll take 2 times the 1, 0 vector, which is 2, 0, plus 4 times the 0, 1 vector, which remember, these are just the standard basis vectors. So 2 times the 1, 0 vector returns 2, 0. 4 times the 0, 1 vector returns 0, 4. And when you add them together, you get 2, 4. And same thing for the 3, 5 vector. And this is the one exception to where you can switch the order of two matrices and guarantee that the result will still be the same thing. Finally, we'll look at something called the transpose. And the transpose is something that we often want to do to a matrix, especially imagine that you have a spreadsheet and maybe along the columns you have various people, people's names, and along the rows you have maybe their age, you have their height, you have their address. And what you want to do is you want to actually see instead of having the people along the columns, you want the people to be along the rows, and you want their data to be along the columns. Well, in that situation, it might make sense to want to transpose the matrix. And what the transpose does is it basically is, if we start off with an m by n matrix, when we transpose it, we'll get an n by m matrix. So effectively, and you can think about this two ways, all of the columns when you transpose it, so this is not A raised to the power of t, the way you read this is A transpose. And you see that the first column, AC, basically laid on its side to become the first row. The second column, BD, laid on its side to become the second row. Now, another way of thinking about that as well is to say it would be identical to conclude that the first row of matrix A becomes the first column of matrix A transpose, and the second row of matrix A becomes the second column of matrix A transpose. And it's a little bit more evident whenever you have matrices that are not square. You can see that these just become the two distinct rows here. And same thing here. And some properties that are useful for dealing with transposes, because sometimes you transpose a transpose. Well, what would happen if we took A transpose and then transposed it again? Well, that means AB would become the first row, and CD would become the second row. And hey, wait a minute, that's just the original A matrix. Now, also, if we take two matrices and add them together, I'll give you an example of B. If we took 1, 2, 3, 4, plus 5, 6, 7, 8, and we wanted to take that result and transpose it, then if we were to transpose them, well, let's add them together first and then transpose. So we'll get 6, 8, 10, 12, and now we want to transpose that, which will give us the first column becomes the first row, so 6, 10. Second column becomes the second row, 8, 12. And if we had transposed them first, I'll do it over here. If we took 1, 2, 3, 4 and made it 1, 3, 2, 4, and added that to not 5, 6, 7, 8, but 5, 7, 6, 8, you can see that we're still doing 6, 10, 8, 12. We're going to get exactly the same answer. For a scalar, scalars usually don't have very dangerous impact, so whether you scale a matrix first and then transpose it, or you transpose it first and then scale it, you're going to get the same result. And finally, if you take a product of matrices and you transpose them, another way to do that is, okay, so if I want to multiply them first and then transpose the product, I could instead transpose B, transpose A, and multiply them in the reverse order. Let's just do a dimensional argument here. If A is 2 by 3 and B is 3 by 17, and we then take the product and transpose it, well, the inner dimensions match, so we'll get a 2 by 17, which will be transposed, and that gives me a 17 by 2 matrix. Now, if I try to do A transpose times B transpose, basically just saying that the transpose distributes, then A transpose is 3 by 2, B transpose is 17 by 3, and now the inner dimensions don't match. However, if I look at B transpose times A transpose, which is 17 by 3 times a 3 by 2, inner dimensions match, and I end up with a 17 by 2 matrix.